We're gonna talk about E! The big famous constant E! Sayo, try calling the definition of E on the top of your head.
Okay, say you have $1 and you put it in the bank. Now say that after each year, the amount of money in the bank will increase by 100%. That is, 100% of the money you currently have in the bank will be added, which is just $1. So by the end of the year, you'll have $2. Now, what happens if instead, every 6 months, 50% of the money currently in the bank will be added to the total? After 6 months, 50 cents will be added to the dollar, making $1.50. After another 6 months, 75 cents will be added. So by the end of the year, you have $2.25. If you do the same with every 4 months and 3.333%, you end up with $1.33, $1.77, $2.37. 25% every 3 months, you get $2.44. 10% each tenth of a year, that's $2.59. 1% every 100th of a year, $2.70. This pattern would not diverge to infinity. Eventually, you approach a number equal to roughly 2.718288182. This is Euler's number, or E.
Good, now you know what the natural logarithm, right?
Yeah, a logarithm is just the inverse of exponentiation. If a to the power of b equals c, then log base a of c equals b. In the case of the natural logarithm, the base is e.
Here's the thing. In calculus, the natural logarithm can be described as the area under a hyperbola between 1 and x. In other words, the integral from 1 to x, 1 over t dt, equals log of x.
Doesn't log of x by itself usually mean log base 10?
I much prefer using that over ln of x, even if it causes some confusion. Anyways, you might be wondering how these two definitions be possibly related at all, and that's today's question. We need to show that the integral of 1 over x is a logarithm and the base of the logarithm is e.
Wait, has it already been 2 minutes into the video? We need to roll the intro now.
Note that this video will not be going into the history of E or the natural logarithm. There are other videos explaining that. Anyways, the most important property of logarithms is this. So, how about we start by trying to add two of these integrals together? What we can do is do a substitution to the second integral. Let u equal ax. Du is equal to adx, and the bounds become ab and a.
Then we can cancel out a on the numerator and denominator.
You're catching on! Now, note that it now has the exact same form as the other integral, 1 over something d something. We can make both of these x and notice that the upper bound of the left integral is the lower bound of the right.
So we can join them together.
So we proved that the function satisfies the property of logarithm, but what if there is another type of function that shares that property?
Well, let's say that there's a function f of x such that f of ab equals fa plus fb. If you raise both sides by some number b, by the laws of exponentiation, b to the f of ab equals b to the f of ab to the f of b. It appears that the new function, call it g of x, satisfies g of ab equals gab. Now, if only there was a function such that if you multiply the inputs and put it in, you get the products of the outputs. Gee, I sure wonder what sort of function—
Sayo, g of x equals x fits the criteria. You know, originally I was supposed to do that gag, but I guess it was more natural for you to end up saying it. Also, any function of the form x to the n fits the criteria.
Oh yeah.
I'll flash the full derivation on the screen. Anyway, since g equals b to the f of x, we can take the logarithm base b to get f of x equals n log base b of x. Note that we're using another property of logarithms. In addition, using a third property of logarithms allows us to get f of x equals log base b to the n of x. Damn it, I got the script wrong. I meant log base b to the 1 over n of x. So in fact, all log functions and only log functions satisfy the criteria. So, now we can figure out the base. Here's the definition for the derivative of log of x. Using the main property of logarithm, we get this, which we can rewrite as this.
We want to get 1 over x, right? So if we multiply the numerator and the denominator with x, we get this. We can then take out 1 over x.
Hey, I wanted to say that. Now, we can see that this part needs to be equal to 1. Let's put the limit inside the logarithm and use the third property of logs. As delta x goes to 0, x over delta x goes to infinity, so we can replace it with n. Looks familiar?
This is the definition of e, and for the logarithm of e to be 1, the base of the logarithm must be e. QED. Wow, we got this one really fast, huh?
Yeah, and since we have the time, there's one last thing I want to show you. Let's say that y equals e to the x. This means that x equals log of y. Differentiating both sides with respect to x, the left-hand side must be equal to 1, and the right-hand side, using the chain rule, is equal to 1 over y times dy over dx.
I think you wrote it the wrong way round.
Oh, whatever. Now, here's the punchline. If you multiply both sides by y, you get dy over dx equals y. And since y is equal to e to the x, the derivative of e to the x is itself.
This isn't just a silly maths fact that makes itself into memes sometimes. I've heard that this has a very useful application in differential equations.
For example, differential equations of this form uses an exponential in its general solution. But I'll leave it to you to figure out.
Come on, you can't just leave us hanging there.
Fine. Just give me a minute. So we have an equation of this form, which almost looks like we can just reverse the product rule. However, to do so, we need to multiply both sides by a function such that if you differentiate it, you get f of x times that function. Fortunately, since the derivative of e to the x is e to the x, we can use the chain rule to show that the derivative of e to the capital F of x plus cx equals f of x times that function. Gosh, that was hard to say. So we multiply both sides by that function, and we can divide e to the cx from both sides to make it easier for us. Integrating and rearranging, you get the general solution for y.
That was interesting. Well everyone, take care and I'll see you in SoME4 episode 7.